Hi, this video introduces the magnetic field and also the magnetic force. So actually, that's the title, magnetic field and magnetic force. So on the one hand, there's going to be a field. So I might depict the field with a field line diagram just like electric field. So let me draw a field. So this is a field line diagram. And you can see that, and I'll direct it. So that here's the field lines. And you can see that the field lines are actually all kind of close to each other over here on the left, but over here on the right, the field lines are further apart. And you'll recall that when the field lines are further apart, the strength of the field at these places is weaker. And when the field is closer, or the field lines are closer to each other, that's how we depict stronger electric field. And then you can see the direction of the field is indicated by the direction on the field lines. Yeah, so stronger and weaker. This is a field line diagram. Okay, so for example, say right here, we could sort of guess that the magnetic field is, say, of this strength, and magnetic field is indicated by the vector capital B. It's a lot like the vector capital E is reserved for electric field, and lowercase g is reserved for gravitational field. But since we're talking about magnetic field, let me erase those other fields and just talking about magnetic field. So the magnetic field here has this arrow, right? I drew it kind of short because this is where the field is weaker. But if I ask, well, tell me about the magnetic field, say over here. Over here, the magnetic field is going to be somewhat stronger because it's in a place where the field lines are closer to each other, and the direction is actually slightly different. It's sort of this direction here. So the magnetic field over here is a bigger value than the magnetic field over here. And more than that, they actually have different directions. This is sort of down to the right. This one is up to the right. Okay, yeah, so magnetic field. You can have lots of fields all together. And that actually might be something that you see on Earth. So for example, this is something of a cartoon drawing. So here is Earth. So Earth has 3 electric fields. Let's say that, for the purposes of argument, let's say that there is just a positively charged section of Earth. So I'm indicating that by it being blue. So it's positively charged. So let me say that that's positive electric charge. And then more than that, though, there is a North Pole and a South Pole. You know that the Earth comes with these poles. Strangely enough, actually, the North Pole is actually magnetic south. So that's weird, but it is magnetic south. And the South Pole, geographic South Pole, is magnetic north. And coming with those North Pole, South Pole designations, there is a magnetic field that goes, there's a field line that goes from the North Pole over towards the South Pole. It comes out of the North Pole and goes into the South Pole, and actually goes all the way through. And it's also over here, right? So it comes out of the North Pole towards the South Pole, but then keeps on going. Can you see these cycles? Goes on the inside of the Earth, it goes from the South Pole to the North Pole, but on the outside of the Earth, it goes from the North Pole over around to the South Pole. And towards the poles, the field is actually quite strong. But when you go way out in space, the field is weaker, right? And we designate that by making the field lines further and further apart. But you can see that the magnetic field is actually quite strong near the poles and weak far away. Okay, but remember the electric field? Let me draw the electric field. Oops, I'll draw it in blue. Electric field lines, right, they point away from positive charge. So I've got this red field line, that's the magnetic field of the Earth. And some reason the Earth is very positively charged over here, so it's got field lines, right, that come out like this. And this is electric field lines, right? And remember, field lines go away from positive charge. And I've got these red field lines. The red field lines are because of magnetism. And just because Earth is verdant, let me, in green, remind you that there is also a gravitational field everywhere around the Earth, pointed towards the center of the Earth, right? Because that's how gravity works, right? And all three of these fields are happening at the same time. And the electric field, the way it works is if you have a charge Q, right, the force on that charge Q by that electric field is just Q times E. And the way that, so this is electric force, right? I'll remind you about gravity. The gravitational force, which is also known as a weight force, right? The way you use it is you just multiply m times g. You take the mass and you multiply by the field. And that's the gravitational force, right? But what's weird is the way that the magnetic field works. It's quite a bit different. So the force by a magnetic field is also a vector, but it actually doesn't just depend on the charge, right? There's going to be a magnetic force on a charge. It also depends on the motion of the charge. So this is V for velocity. So it depends on the velocity of the charge. So you take Q times V, but then it's worse than that. It's the vector cross product with the magnetic field, B. And this is a force law. And in SI units, the force will be in newtons, the charge is in coulombs, the motion is in meters per second. And so whatever the units of the magnetic field are, I've got to be able to, that they're actually symbolized by capital T. This is the SI unit of magnetic field strength. It's referred to as the Tesla. And the Tesla times the meter per second times the coulomb is the Newton. That's the SI unit. So we can say, we can define the Tesla. So let's define the Tesla T, where 1 Tesla is equal to, right, solve for Tesla, it's the Newton second per Coulomb meter. Like this. So that's the definition of the Tesla. So I'll give you a 3 bars equal sign for definition. So this is the unit, right? It's the SI units of magnetic field strength. And in order to understand how magnetic field has anything to do with force, right, I have to multiply magnetic field strength in Tesla by coulombs and speed, right? Charge and speed. Yeah, so this right here is a very important equation. It's the magnetic force law. And it tells you about the force on a charge Q whose motion is velocity V through magnetic field B. and it's a vector cross product. And that's an important detail, vector cross product. Okay, so here is, so we have to build a skill, right? So that's a skill that we need to build, and I'm going to show you some ways to calculate this force vector. So it's the magnetic force, Q, V cross B, where, for example, if you're given the charge and the velocity of that charge and the magnetic field vector, you can calculate the magnetic force, right? So we'll have some examples in a following video.